STS-116, also known as International Space Station Assembly Mission 12A.1, is considered by many to be one of the most complex station assembly missions ever. That's due largely to the extremely small margin for error in the vast array of activities.
This is the flight when the crew and the ground have to be completely in sync because of the time pressure that exists, especially on the second and the third spacewalks. The crew and the ground have spent a lot of time training, probably more than any other flight in recent history.
The main focus of the mission is to maximize the station's long-term ability to produce and distribute electricity. This calls for an update of the station's electrical and thermal systems. Prior to STS-116, the electrical power system has been in a temporary setup, with primary power routed directly from the solar arrays on the P6 truss to conversion and distribution units on the Destiny Lab and the Z1 truss. Rewiring the station will place it into its designed configuration.
The space station was designed around a truss, what we call a main power truss, which spans space station and has solar array wings on the end of it. Right now, one of those solar array wing sets is actually situated on top of space station in a temporary place. What we're going to do is we're basically going to unplug space station from that truss and plug it into this main truss.
The main design has these boxes called the MBSUs, the main bus switching units. They are in the S0 truss and they have never been used. Those main boxes have the capability of having primary power with backup power and cross-strapping so that if you're having a problem getting power from one set of arrays, you can talk to another MBSU and just very simply swap different power channels around.
The process of rearranging the electrical system to make it more powerful and versatile is initiated by Mission Control the day before the second spacewalk. That's when ground controllers plan to retract a solar array on P6 to prepare for the power changes and the rotation of the recently installed P4 arrays.
And the reason the retraction was important is the P6 arrays like this, the P4's array is like that. The P4 array, to track the sun and get electrical energy, has to be able to rotate 360 degrees.
So the ground controls, they will first do some kind of power reconfiguration such that the power which used to come from this one we're retracting now kind of comes from somewhere else. Then they will do most of the commanding.
And maybe most of the worrying, since they are uncertain how well an array that's been fully extended and exposed to the space environment for so long will fold back up. If the array doesn't fold up as planned, options include having spacewalkers manually retract it using a power tool or leaving it partially retracted, but still giving the P4 arrays enough room to rotate. The rewiring of the electrical system starts the next day. Spacewalkers will undo the temporary connections and then make the permanent connections. But the most unpredictable aspect of the day kicks in before the spacewalk starts, when Mission Control shuts down about half the station's power.
You don't want to create a shock hazard for the crew, so we have to turn off those lines before they do that, the demate and the remate from the early to the permanent system.
A jumper cable will be installed inside the station so critical systems can be powered by the half of the electrical system that's still operational. With half the power system off, the crew and Mission Control will have a lot of things to watch closely.
The space station has got redundancy in that it's got 4 basic channels, and we number them 1, 2, 3, and 4. So when we turn this all off, that means we just lost redundancy on all of those systems, so I'm now 0 fault tolerant.
There's all sorts of thermal clocks and you know, I have one watch on here, but maybe I'll have 4 or 5 that I got running for different thermal clocks, either for a tool or for a system that doesn't have what we maybe call keep alive power, power that keeps heaters going so it doesn't get frozen up.
The concerns are just as prevalent when ground controllers turn everything back on.
When we power this up, there's a lot of boxes there which has never been used before. And it might even be that during the EVA, when we do the power down, when and then power it up again, they say, oops, this one doesn't work.
And so that's when we start doing different spacewalk contingency procedures to either replace boxes, fix boxes, whatever we need to do to get that system up and running.
To complicate things even further, in a high-tech Catch-22, the thermal control system that cools the electrical relay units, or MBSUs, needs to be brought online. But that system is powered by the same electrical units it's designed to cool. The MBSUs can't operate too long before overheating, so getting the cooling system running involves pressure in more ways than one.
We power up, now the pressure's on the thermal control officer to get the pump running. It has to come up to a certain pressure first before you can then push the fluid through the system.
The overhaul of the electrical and thermal systems will be completed the following day. When finished, it will increase the number of U.S. solar arrays powering the station from 2 to 3. Another job for the crew will set the stage for even greater increases in power for the station. They will install a new segment of the station's girder-like truss called the P5 short spacer.
We call it a spacer, and in essence, it goes at the end of P4, which is another truss structure which has a pair of solar arrays.
To attach the spacer, it will first be moved into a pre-installed position, just inches from the P4 segment to which it will be attached. The arrays on P4 will be locked in place to give the crew room to work.
The P3, P4 solar array wing is live at the time, so there's going to be some black boxes on the end of P3, P4 that are live powered. And so with that clearance, the biggest worry is that you don't hit the box that has the live power on it.
Because TV camera views are not available, the spacewalkers will verbally guide robot arm operators as they move the spacer into its final position.
It's really like almost threading a needle through a needle eye to get this P5 in place. At some place the margin is only, I think the nominal would be 7 centimeters.
The new segment will allow for the eventual relocation of the P6 and its solar arrays. The spacer segment provides separation so that the P6 and P4 arrays can rotate without hitting each other. A rotation of another type on the mission takes place when Sonny Williams swaps places on the space station with flight engineer Tomas Ryder. Although this is only a partial station crew change, it's the first by a shuttle since the Columbia accident, enabling NASA to maintain an American presence on the station without sole reliance on the Russian Soyuz vehicle.
I think probably the most significant thing for us to take from the exchange of Thomas Ryder for Sonny Williams is that we're back in business.
And what that means for NASA is getting back on track to the task at hand of not only completing space station, but bolstering its potential for this and future chapters of human spaceflight.